So I'm currently teaching a group theory class, and a nice final project for such a class is to classify as many groups of small order as possible. And well, there are several tools for this involving the CELO theorems, which I have videos about already. But another one of the tools is something called the semidirect product. So I thought I'd make a video about that. Okay, so let's dive into the definition. So let's suppose we've got groups G and H. And we also have a group homomorphism from H into the automorphism group of G. I said into like it's got to be injective, but it doesn't have to be injective. So anyway, a group homomorphism from H to the automorphism group of G. And we'll denote this map as H is being sent to phi sub H. So this phi sub H, recall, is an automorphism of G, which means it takes inputs from G and gives you outputs in G. Okay, then we're going to define the semidirect product of G and H with respect to phi by the following data. So as a set, it's simply equal to G cross H. So the Cartesian product of those two groups thought of as sets. But then the operation is a bit tricky. So we take G1, H1, and we're going to combine it with G2, H2, and we're going to get the following. So in the first entry, we'll have G1 times phi of H1 evaluated at G2. So recall that phi is an automorphism, so that's going to give you an element of G right here. And then the second entry is simply H1, H2. So you can kind of think of it like this. The multiplication of the G component is being twisted by the elements in H, whereas the H components are untwisted, if you will. So I guess a logical thing to look at here is there some sort of setup where you get a twist in both? And there is. That's called the wreath product. I'll let you look that up if you want to. Furthermore, let's notice that if we have a trivial homomorphism here, in other words, the homomorphism that takes H simply to the identity map, then this operation over here turns into just G1, G2. So that means that the normal direct product is an example of the semidirect product where we've got a trivial map from H to the automorphism group of G. Okay, so maybe the first thing we'd like to check is that this actually forms a group. Now, in order to have a group structure here, we need an identity inverses, and then you also need associativity. Maybe we won't check that. I'll let you guys check that if you want to. It's just a fairly simple calculation. Okay, so let's look at the identity first. And well, if everything is nice, the identity should kind of be obvious, and it is. So let's take GH, and we're going to combine it with the identity in G and the identity in H. So if everything is working out nicely, that should be the identity. Okay, so that's going to give us the following. So we'll have G, and then we'll have phi sub H evaluated at the identity. And then over here, we'll have H, well, times E sub H. But look at this. We know that any homomorphism takes the identity to the identity, and phi, well, is a homomorphism. Well, phi sub H is an automorphism, which is a type of homomorphism. So that means here, well, we're going to get the identity on G, I should say, but then that's going to give us just simply GH. And I guess we have to check it in the other direction as well, or in the other order. So EG, EH times or star GH will simply be equal to EG, and here we're going to have phi sub EH evaluated at G, and then over here we have H. But the homomorphism attached to the identity element will necessarily be the identity automorphism, because that's the identity element of the automorphism group. And the identity always has to map to the identity. So that's simply going to give us G in that component to get combined with this EG, which is going to leave us with a G as necessary. So that tells us that our identity here is simply this ordered pair of both identities, as we would like. Okay, so now let's look at inverses. So what we want is to find an xy in G, well, I'll write semidirect product H, so that if we do GH star XY, we get the identity in G and the identity in H. That would mean that XY is the inverse of GH. But let's observe that that is equivalent to having G and then VHX, comma, HY equal to this identity structure over here. But look, that's equivalent to G, VHX being equal to the identity on G, and HY being equal to the identity on H. But now we'd like to quote unquote solve that for X. So now that's going to give us VHX is equal to G inverse. But now we'll operate on that with the inverse of VH. So VH is known to have an inverse because it's an automorphism. And that inverse will simply be phi attached to H inverse. So that'll give us X equals VH inverse G inverse. But then over here it's simpler. We just simply have Y equals H inverse. So I guess we could put all of that together over here, and that would be the inverse of GH is equal to, well, let's see. It's going to be VH inverse G inverse, and then H inverse. Okay, nice. So anyway, we've shown that there's an identity element, and we've got inverses for everything. Now, I'll let you check associativity on your own, like I said before. Okay, so now let's see if we can jump into some examples. Okay, so we're going to jump right into a fairly general example, and then we'll look at some special cases of that. So we want to take the semidirect product of the integers modulo m with the integers modulo n. But in fact, in this case, it's a little bit better to work with the multiplicative version of those groups. So sometimes those are just called the cyclic C groups, or Cm and Cn. So here we've got Zm is isomorphic to Cm, but what's Cm? Well, it's going to be a cyclic group generated by X with m elements. So those m elements are Ex, x squared up to x to the m minus 1. So essentially you're just moving the addition of Zm into the exponent. And then we similarly have Zn, which we'll say is isomorphic to Cn, and we'll say that's generated by Y. Okay, nice. So now what we need is some sort of map from where? Well, it's got to go from Zn, or I guess I should say Cn here, because what we're really doing is that this should be isomorphic to Cn semidirect product over phi with Cn. This first one should have been an M. Because again, like I said, it's a little bit nicer here to work with the multiplicative versions of the groups. Okay, so anyway, looking over here at our definition, we need a homomorphism phi from Cn into the automorphism group of Cm. But let's talk this through. That is isomorphic to the automorphism group of Zm, because Cm and Zm are isomorphic. But then by a fairly standard result, it was actually a homework problem for my students, that's isomorphic to the group of units Um. So now, well, what are we going to do? So we're going to take our element Y inside of Cn, and where are we going to send it? Well, we're going to send it to something that we'll call phi sub y, where phi sub y takes x to what? Well, it's going to take x to the k, where, let's see, k is essentially in um. But to be inside of um, the GCD of m with k needs to be equal to 1. That's like the entry fee to be inside of um. Now, you can check that this, in fact, is an automorphism. In fact, this sort of exponentiation is maybe always a homomorphism, but it's an automorphism exactly when k is relatively prime to m. That's pretty easy to show here. Well, and you might say, well, is that the only restriction on K? And in fact, it's not the only restriction on K. We can develop another restriction on K as follows. So maybe I'll just put that here kind of as a little bit of a note. It'll be pretty important though. And that is, if we take X, that's going to be the same thing as the identity applied to X. But notice that y to the n power is the identity. And so if you apply the phi attached to the identity, you get the identity. So in other words, y to the n is the identity because we're in Cn. But then phi attached to the identity, because this is a homomorphism, is the identity automorphism. I know a lot of stuff's going on here, but needless to say, this is simply the identity map. But then since phi is a homomorphism into the automorphisms, what we can do is take this product down here that is happening within Cn and bring it into the product in the automorphism group, which is simply composition of functions. So that's going to give us phi composed, or phi sub y composed with phi sub y, so on and so forth, phi sub y, all applied to x. But what does that give us? Well, notice the first one is going to give us x to the k. And then the second one is going to exponentiate that to the kth power. Then the third one is going to exponentiate that to the kth power, and so on and so forth. So what we're going to have is this like power tower like this of a bunch of k's. And how many k's are we going to have? We're going to have exactly n k's. So that means in the end, we're going to get x to the k to the n. Okay, nice. But now let's look at the extreme left and right hand side. We have x is equal to x to the k to the n, but what that tells us, x to the k to the n minus 1 is equal to the identity. That's just by multiplying by x inverse on both sides. But then we know the order of x is m. That's because x is a generator of Cm. So if we're raising x to something and we're getting the identity, that means that this thing in here is a multiple of the order. In other words, we have m divides k to the n minus 1. But that tells us that k to the n must be congruent to 1 modulo m. So we get something like that. So those are our two rules on this power of k that's defined by this phi sub y automorphism. It has to satisfy the GCD of m with k is 1, and it has to satisfy this rule that k to the n is congruent to 1 mod m. But as long as you have that, you have a proper setup for the semidirect product. Okay, so now let's see what we can get out of this. So here's what I'm going to do. Let's go ahead and set A equal to XE, and we'll set B equal to EY. So I think it stands to reason that it's pretty clear that A and B will generate this semidirect product. So I'll just put that note here, that this semidirect product, Cm, let's see, semidirect product over phi with Cn, is kind of clearly generated by AB. That's because as a set, it's just a power of x and a power of y. But now let's observe the following. Let's notice that A to the m is equal to x comma e to the m power. But notice there's no component in the second entry in order to twist the multiplication in the first entry. So this is just going to give us x to the m and the identity. But since x is in Cm, that means x to the m is the identity. So this just gives us the identity and the identity, or the identity. So I'm using e over and over and over for the identity, but just keep the context straight. So in the first entry, it's the identity for this cyclic group. The second entry, the identity for this cyclic group, and outside of the parentheses, it's the identity for the entire semidirect product. Okay, so that's what we've got there. And then very, very similarly, Let's observe that we have A sub n, or sorry, I should say B sub n is also equal to the identity. So we've got this rule that our semidirect product is generated by A and B. A to the m is the identity, and B to the n is the identity. It's like our generator from Cm and our generator from Cn. Now let's look at how they commute, or how they maybe lack commutativity. So let's do that by looking at the following. B, A, B inverse. So I think looking at this will kind of tell us how they fail to commute. So let's observe that that's going to be E comma Y, and then X comma E, and then let's see, E comma Y inverse, which is really y to the n minus 1, given we're in this cyclic group of order n, but let's just leave it as inverse for now. But now we can push these together without any twisting, and that's because we're always twisted by this entry right here if we're combining from the left like this. So let's do that. That's going to give us E comma Y, and then it'll give us X comma Y inverse, so something like that. And now we'll apply the rule for these two. Now we do get some twisting because of this right here. And that's going to end up giving us phi sub y applied to x, and then comma y inverse. But observe that that's simply equal to phi sub y applied to x was x to the k, and y inverse is the identity. So in the end, we're going to get what? That's going to be a to the k using our rule from before, using this definition right here. So let's see if we can put that together. Now we see that B inverse is equal to a to the k. In other words, BA is equal to a to the k times B. And again, that's where we've chosen k satisfying these two rules right here. Get this cleaned up, and then we'll summarize this setup right here. All right, so here's a summary of what we just found. So if we set A equal to XE and B equal to EY, then we just showed that CM, semidirect product over phi with Cn, is generated by A and B, and then A and B satisfy the following rules. And these rules fully give us the structure of our semidirect product. In other words, they completely determine this structure. So we've got A to the M is the same thing as B to the N, which is the identity. And then we have BA equals A to the KB. And that's, of course, where phi sub y, so in other words, the automorphism attached to y evaluated at x is x to the k, where k to the n is congruent to 1 mod m. Notice I left off this fact that the GCD of k with m is 1, and that's because that's required for this to occur in the first place. Okay, so now let's look at a special case. So let's look at CM semidirect product with C2. Okay, so that means we're going to get the following setup. So just following this exactly, that's just going to be generated by A and B, and we're going to have A to the M is equal to B squared, which is the identity, and then we're going to have BA is equal to A to the K B. And let's go down here and notice that we need the following. We need K to the squared, because it's K to the n power, to be congruent to 1 modulo M. Okay, great. Now, I'd like to observe that, there might be several different solutions to K squared congruent 1 mod M if M is composite. And I'm not going to check this super carefully. All of them except for the case when K is equal to 1. And when K is equal to 1, we just get the normal cross product, or the direct product, will give us isomorphic results. So let's go ahead and take K to be minus 1, because K equals minus 1 is clearly something that's going to give us this K squared is congruent to 1 mod M. I think that's pretty clear. So let's observe that means we have the following. We have this group satisfies this new rule. Well, new, it's just specialized, that BA is equal to A inverse B. But then, using the fact that the order of A is m, that means that BA is equal to A to the m minus 1 B. And perhaps this looks kind of familiar. Let's perhaps set B equal to S and A equal to R. And now observe that we have S squared is the identity, we have R to the m is the identity, and then after that we have SR is equal to R to the m minus 1 S. But those are exactly the defining rules for the dihedral group. Perhaps this one is written kind of backwards as how you would generally write it, but you can move things around here to show that RS is equal to SR to the m minus 1. That's equivalent. So all of that is to say that we have CM and then semidirect product with phi, and the phi doesn't matter here, with C2 is isomorphic to the dihedral group DM. So, well, it turns out that we knew about a semidirect product all along because the dihedral group is probably pretty familiar. Okay, so now let's look at another special case of this. So a natural special case to look at would be if you have CP and CQ where P and Q are primes. And well, let's see, that essentially has the same sort of setup as we had before. CP, semidirect product CQ. Well, it'll be generated by A and B, where A to the P is the same thing as B to the Q is the identity. And then we have BA is equal to A to the KB, where automorphism phi sub y takes x to the k, where again, k to the q is congruent to 1 mod p. Okay, so that's a mouthful, but that's essentially what we had before. Now to be real concrete, let's look at a special case of this. So let's look at C7 semidirect product with C3. So just writing this down, using everything that we've done so far, this is going to be generated by A and B. We have A to the 7 is the same thing as B cubed is the identity. And then we'll have B to the A is equal to A to the 4th times B. And this is because we could have 4 to the power 3 is in fact congruent to 1 mod 7, which is what we need for this to work. Now you might say, well, are there other choices of numbers that we could put here where we raise them to the 3rd power and we get something congruent to 1 mod 7? And yes, there are. For example, 2. If you take 2 cubed, you get 8, which is 1 mod 7. That being said, those will all give you isomorphic structures here. So I'll let you check that those will give you isomorphic structures. Okay, well, I'd like to also observe the following, and that this is isomorphic to the following group of matrices. And so it's going to be generated by this 3x3 matrix 1, 1, 0, 0, 0, 1, 1, 0, 0, and this other 3x3 matrix 1, 0, 0, and then 0, 0, 1, and then 0, 1, 1. But these don't live with real entries, they live with entries in Z2. So we could denote that by just saying that this is inside GL3 Z2. Now, how would you see that these are isomorphic? Well, you would check that one of them is raised to the 7th power to give us the identity. The other one cubes to the identity, and then they satisfy this commutation relation. Okay, so if you remember about direct products of groups, there were internal and external direct products of groups. Well, it turns out that there are internal and external semidirect products of groups as well. This is the external semidirect product. Now let's look at the so-called internal semidirect product. All right, so let's look at this nice theorem which will allow us to take some information about a group and then express it as a semidirect product of its pieces. So let's say that G is a group, H is a subgroup of G, and N is a normal subgroup of G. And then we also know that H intersects with N only in the identity, and G is equal to this product of groups NH. Now we know that NH is a subgroup because N is normal. Remember, that's a condition for that type of thing to be a subgroup. But we're also supposing that it's the whole group. Then G is said to be an internal semidirect product of H and N. That's the setup that gives us this. And furthermore, since it's an internal semidirect product of H and N, it's in fact isomorphic to the external semidirect product of N and H, where phi sub H evaluated at N is equal to Hn H inverse, where the phi sub H is associated to this kind of automorphism right here. Okay, nice. So now, how might this go? Well, it's actually pretty straightforward. It almost does itself. So let's define psi from this semidirect product with N and H to G, where we take psi of N comma H and we simply send it to NH. So that's clearly going to be an onto function, just given the structure of G here. We just have to check that it's a homomorphism. Since it's kind of obviously onto, then since these groups are of the same size, we know that it'll be a isomorphism. Okay, so let's get to it. So let's do psi of N1 H1 combined with N2 H2. Let's do this combination in the middle first. So this is going to be psi of N1, and then we're going to have phi of H1 evaluated at N2, and then here we'll have H1, H2. That's just using this rule over here. But now expanding this out inside of psi, we're going to get N1, and then after that, we're going to have H1, N2, H1 inverse. And then still in that second entry, we have H1, H2. But now we're going to apply the psi map, and that's going to give us N1, H1, N2, H1 inverse, H1, H2. But let's observe that that puts an H1 and an H1 inverse right next to each other and leaves us with N1, H1, N2, H2. In other words, psi of N1, H1 times psi of N2, H2 as needed. Okay, good. So now we can use this to, like I said, break groups of certain orders into semidirect products of subgroups. So let's look at an application. All right, so let's go through an application, and part of this we've done before, but it's good to see it again. So let's say that G is order PQ, and P and Q are primes where P is less than Q. So these are distinct primes. Then let's set NP equal to the number of CeLO P subgroups and NQ equal to the number of CeLO Q subgroups. Furthermore, by the third CeLO theorem, we know that NP has to divide Q and it has to be congruent to 1 mod P. That means that NP is either 1 or Q. Notice that Q is bigger than P. We're going to use that here. And then NQ has to divide P, and NQ is 1 mod Q. Now, since Q is bigger than P, it cannot be equal to P, so that means NQ has to be 1. But that means that there's a unique CeLO Q subgroup. So let's get that written down. Maybe we'll write that here. So there's always a unique CeLO Q subgroup. And maybe we'll call that thing Q. And since it's a unique CeLO Q subgroup, that means it is normal. We talked about that previously when we just talked about the CeLO theorems. Okay, so let's hang on to that. So regardless of the group, it's got a normal CeLO Q subgroup. Okay, so now let's look at this first case when NP is also equal to 1. So that means in this case, there is a unique CeLO P subgroup. We'll call that P. And now that's going to be normal in G as well for the same kind of reason. Okay, but now let's observe that tells us that G is equal to the product of P and Q. And well, why is that? And that's because the order of this product, well, first of all, it's a subgroup because, well, at least one of them is normal, and in fact, they're both normal. And then furthermore, the size of PQ is the size of P times the size of Q over the size of the intersection of P and Q. But since they are prime groups of, let's see, distinct orders, that means they intersect trivially, which means that this is simply equal to P times Q, which is the order of G. So that means we've got a subgroup, which is the size of the whole group, so it's the whole group. But then by some stuff that we proved, before, we know that if both of these are normal and we have this setup, this is isomorphic to just simply the direct product of P and Q. But that's simply ZP cross ZQ. Okay, nice. So nothing is new here. And in fact, in the setup where you have G as order PQ, this is always a possibility to have this ZP cross ZQ, which I guess I should point out just for the sake of completeness. This is the same thing as ZPQ, given that P and Q are relatively prime. Okay, so now let's look at the second case. And now this case is not always possible. This is when NP is equal to Q. And so let's point out that this is only possible if Q is congruent to 1 mod P, which is definitely something that can occur. For example, that case of 3 and 7 that we just went over, that is a case like this. But now observe that we still know that G is equal to PQ internally. But now we only know that one of them is normal. And since we only know that one of them is normal, then they don't decompose as a direct product, they decompose as a semidirect product. And so that this is isomorphic to Q semidirect product with P. And I'm careful to put it that way because notice in this setup over here, the normal subgroup is the H one, and that's how we had it for that theorem. And so since Q is the normal subgroup, we put it on the left like that. That's kind of important. Okay, cool. But observe that this is isomorphic to ZQ semidirect product with ZP. And you might say, well, there could be a bunch of these that depend on this homomorphism phi. Now, we're not going to show this, but in fact, these are unique. Whichever phi you choose, as long as it's not the trivial homomorphism, you do end up with an isomorphic structure. Okay, so well, what does that tell us? Well, that tells us if we've got a group of order PQ, then in fact, it must be of one of the following isomorphism classes. It can be either ZPQ, or it can be the semidirect product of ZQ with ZP. And, well, we saw that actually really concretely with groups of order 21 just like a minute ago. Okay, so now I'm going to leave you with one exercise to explore this. Okay, so this is kind of a big exercise, but you'll get a lot of practice out of it. And that is to find all groups of order PQ where the product PQ is less than 100, and P and Q are both primes. And when I say this, I mean not just classify them as a direct product or a cyclic group, and then also a semidirect product, but go ahead and find the presentation or the generators and relations form of each semidirect product. And that's a good place to stop.